The first hint Enrico Fermi had that the world was malleable, that it could be reshaped through intellect, came during his childhood in Rome. He was walking along the Tiber River with his older brother, Giulio. The river seemed to debate with the stones lining its banks in slow, deliberate motions. Boats drifted by, resembling ideas still searching for their purpose. Giulio often posed questions that seemed simple on the surface, but revealed unexpected depths when you try to answer them honestly. "Why does the water keep flowing?" he once asked, even when it appears weary. Enrico, at 12, didn't reach for a word like gravity, not yet a staple in his vocabulary. Instead, he picked up a small stick, released it, and observed its journey downstream. "Because it can," he said, and then, after a reflective pause, "and because the river is eager to reach another place." Before we get into the main content, please consider subscribing to my channel, giving a like, leaving a comment, and share to support me in bringing more great videos to you. Thank you so much. Giulio laughed, a sound that made Enrico feel as though he'd unlocked a secret. He would later understand that physics largely consisted of that feeling, articulating a statement that resonated with the universe itself. In those formative years, he amassed books with the same fervor that other boys collected stamps. He claimed a quiet corner in their apartment, a desk perpetually dusted with pencil shavings, and a mind that seemed to ignite the moment he sat down. When Giulio passed away unexpectedly, succumbing to a swift and merciless illness, the apartment transformed into an alien landscape. Their mother's grief hung heavy, a palpable atmosphere. Their father retreated into longer work days to avoid inhaling it too deeply. Enrico, adrift in this altered reality, gravitated toward numbers, toward the certainty they offered, toward subjects that didn't vanish without warning. He sought solace in reading, hoping to quiet the air. One day, a family friend, noticing the boy's restlessness, offered him a university physics textbook, intending it as a distraction. Instead, it became a gateway. Fermi opened it and stepped into a realm where sadness could be held at bay through equations. He didn't simply read the book. He devoured it, scrutinizing derivations as if tasting food for freshness. He began tackling problems designed for students years a senior. When faced with a puzzle, he wouldn't rest until he'd unraveled it. It wasn't merely stubbornness, but a deep-seated hunger to understand what fundamental rules remain when everything else crumbled. By his late teens, he was already becoming a legend among professors, a student who could arrive with a question and leave having introduced a novel approach. He earned a scholarship to the Scuola Normale Superiore in Pisa. The train journey marked his first real departure from Rome. As he watched vineyards and dusty villages blur past, he sensed the weaving of a new chapter in his life. Pisa offered a crisp, salt-tinged atmosphere, echoing corridors, and instructors who were both delighted and slightly intimidated by his rapid pace. Physics, at that time, was undergoing a transformation that felt like the earth shifting beneath your feet. Classical mechanics still served perfectly for planets and pendulums. But within the atom, the established laws began to act like polite guests who suddenly refused to abide by the house rules. Quantum theory, still nascent and somewhat unruly, was sweeping across Europe. Fermi encountered it as if discovering a language he was always meant to speak. He traveled to Göttingen and Leiden, listening to the leading figures in the field, scribbling notes in a small, almost timid script. What distinguished him wasn't just brilliance, but clarity. Other theorists constructed elaborate towers of symbols. Fermi built bridges connecting symbols to reality, insisting they be sturdy enough to traverse without fear. In the 1920s, he returned to Italy and assembled a brilliant group of young researchers, later dubbed the Via Panisperna Boys by the press, named after the street where their institute was located. Their lab was modest in terms of equipment, but rich in laughter, debate, and cigarette smoke. They worked in harmony, like musicians who had finally found their shared rhythm. Fermi led without explicitly declaring himself the leader. He possessed a calmness that simplified complex ideas. When presented with messy data, he would tilt his head, glance at it once, and suggest we try this, as if the solution were patiently waiting at the edge of the table. Then came the neutron. In 1932, James Chadwick in England identified the neutron as a neutral particle within the nucleus. To Fermi, it was like being handed a new kind of key, A neutron carried no electric charge, allowing it to slip into nuclei unimpeded, unlike positively charged particles which face repulsion. This suggested the possibility of altering atoms more easily, bombarding them with neutrons, destabilizing them, and observing their decay into new elements. Even the phrase was alluring, new elements. It evoked alchemy, but this time the spellbook was real. Fermi's group commenced experimenting almost immediately. Using radon and beryllium, they constructed a neutron source, crude by later standards, and began firing neutrons at various materials. Their initial findings were perplexing, fascinating, and sometimes usefully flawed. The lab buzzed with the clicks of Geiger counters, the quiet routine of recording times, and the sudden silences that followed surprising measurements. Fermi often paused at a chalkboard, hands in his pockets, eyes half closed, before writing a line that brought order to the chaos. One afternoon, they observed something peculiar. Neutrons appear more effective at inducing radioactivity when slowed down. This defied intuition. A faster bullet should logically hit harder. Yet, within the atom's strange interior, slow neutrons were more readily captured. The group tested this by placing paraffin, a substance rich in hydrogen, between the neutron source and the samples. Activity increased. Fermi blinked, then smiled with a quiet joy. He had uncovered a quirk of nature that had eluded everyone else. Moderated neutrons were better wanderers. They lingered and were invited into nuclei. This discovery would later form a fundamental principle of nuclear technology. Fermi didn't offer grand pronouncements. He was a man who valued practical steps over rhetoric. But in Italy, as the decade progressed, the atmosphere outside the lab grew heavy in a different way. Fascism was tightening its grip. Anti-Jewish laws loomed on the horizon. Enrico's wife, Laura, was Jewish. Their family felt the lengthening shadow creep through their home like winter seeping through walls. In 1938, Fermi received news that he had been awarded the Nobel Prize for his work on induced radioactivity and the discovery of slow neutrons. The prize served as a spotlight, offering a degree of cover. He and Laura decided that after the ceremony in Stockholm, they would not return to Italy. On a frigid December day, they boarded a ship bound for America. Rome receded behind them like a painful memory locked away in a drawer. Fermi stood on deck, the sea wind whipping his coat, thinking not of the past, but trajectories. What could be built? What could be proven? What new puzzles awaited? He couldn't yet foresee that the key he had discovered, the neutron slowed by paraffin, the nucleus coaxed into change, would soon unlock a door so immense that the world itself would have to step through. The ship sliced through the fog, and the future, like the ocean, appeared calm only from a distance. New York greeted the Fermis with a relentless energy. It was 1939, and the city felt like a machine that had learned to sing. Subways rumbling below, radio spilling jazz into doorways, steam rising from manholes as if the ground itself was deep in thought. To Enrico, this cacophony was less a distraction than a testament to human vitality. He had crossed an ocean, not only to escape danger, but to keep his science alive in a place where it could flourish. Columbia University offered him a desk, a laboratory, and most importantly, colleagues who shared his language of curiosity. The world of physics in America was younger than Europe's, still developing its traditions. This youthful openness suited Fermi. He gave lectures that students later described as walking into a clear room. He didn't embellish or dramatize. He would start with a simple concept, then add layers, mathematics, assumptions, consequences, until the entire structure stood clearly in your mind, like a well-engineered bridge. But the atmosphere in physics was not purely academic. Across the Atlantic, war was becoming inevitable. In the months following Fermi's arrival, news traveled faster than ships. Germany had invaded Poland. France and Britain had declared war. Rumors circulated through labs about the potential ambitions of Nazi scientists. Then, in early 1939, reports from Europe struck like a shattered glass. Otto Hahn and Fritz Strassmann had bombarded uranium with neutrons and discovered lighter elements where they shouldn't have been. Lise Meitner and Otto Frisch interpreted the results. The uranium nucleus was splitting, fission, releasing tremendous energy and, crucially, more neutrons. To Fermi, the word fission wasn't a shock, but But a sudden realization. He had been unknowingly heading toward this gateway for years. If fission released neutrons, and those neutrons could trigger more fissions, then something extraordinary was possible. A self-sustaining chain reaction. Nature, under the right conditions, could ignite a fire that sustained itself. He wasn't alone in this realization. Leo Szilard, intense and restless, had already been contemplating chain reactions. He approached Fermi with the urgency born from envisioning consequences too vast for an ordinary day. Together with other émigré scientists, Eugene Wigner, Edward Teller, they began to ask the most fundamental question that can alter the course of history. Can we control it? Control was Fermi's defining word. He distrusted sweeping visions that skipped the necessary steps. First, we must know if it is possible in principle, he said, then if it is possible in practice. His mind worked with the precision of a meticulous craftsman. A chain reaction required sufficient fissile material, arranged so that, on average, neutrons produced more than one new fission before escaping. The average was paramount. If it was less than one, the reaction fizzled out. If it was more than one, it grew exponentially. The point between these two possibilities was a precarious balance known as criticality. The problem was both abstract and practical. Uranium came in different isotopes. U-235 fissioned readily. U-238 mostly did not. Natural uranium contained only a small percentage of U-235. To achieve a chain reaction with natural uranium, a method for slowing down neutrons was needed, because slow neutrons were more likely to be captured by U-235 rather than lost. Fermi already held that secret from his time in Rome, moderation. So the central question became, what is the most effective moderator? Hydrogen in water slowed neutrons, but water also absorbed too many. Heavy water absorbed fewer, but it was scarce. Graphite, a form of carbon, showed promise. If purified sufficiently, the obstacle lay in trace impurities like boron, which readily absorbed neutrons. Fermi approached this task with the patience of someone who had spent years deciphering the universe's subtle clues. He constructed exponential piles in improvised rooms, stacks of uranium oxide and graphite blocks arranged in carefully designed lattices, with detectors to measure neutron multiplication. The term pile seemed casual, like a child's tower of toys. Yet each pile represented a precise question posed to nature. He would add layers, measure the changes in neutron intensity, plot the data, and infer whether a larger version could achieve criticality. It was quiet work with profound implications. In the evenings, the scientists gathered in apartments and cafes. The aroma of coffee mingled with cigarette smoke and the weariness of individuals who felt the relentless pressure of time. America wasn't yet officially at war, but everyone in that circle understood the war was already encoded in their equations. Szilard drafted a letter warning President Roosevelt of the potential for a German bomb. Einstein signed it. The government began to pay attention. The endeavor that would become the Manhattan Project was still in its nascent stages, but it had been conceived in fear and calculation. Fermi was recruited to a more focused program at the University of Chicago and the newly established metallurgical laboratory. Chicago in winter was a different kind of ocean. Flat streets swept by wind, a sky that felt close enough to touch. The university offered basements, storage rooms, any available space that could be adapted. Fermi didn't mind the modest setting. He had learned long ago that the size of the room was less important than the quality of the thinking within it. They selected an unused squash court beneath the stands of Stagfield for their main experiment. It was an unlikely birthplace for a revolution. A court meant for bouncing rubber balls, now empty and echoing, with a high ceiling and the scent of aged varnish. Workers carried in thousands of graphite blocks. Others brought uranium metal and uranium oxide, packed into cans and molded into shapes that fit the lattice. Everything was done meticulously and with an inventive spirit. They weren't building a cathedral. They were building a question. Fermi designed the structure, a massive, roughly spherical pile of graphite with uranium embedded at regular intervals. A sphere minimized surface area, reducing neutron leakage. Control rods made of cadmium, exceptionally effective at absorbing neutrons, could be inserted or withdrawn to regulate the reaction. Instruments would monitor neutron levels. Safety systems, including an emergency rod nicknamed Zip, were rigged with ropes, like theatrical props ready for the most consequential performance imaginable. As blocks were stacked higher, the pile resembled a dark beehive. It was called CP1, Chicago Pile 1. Fermi walked around it slowly, verifying numbers, occasionally adjusting a placement with a subtle gesture. His calmness was infectious. Even those burdened by the gravity of their undertaking found themselves breathing more easily in his presence. On December 2nd, 1942, they were prepared to pose a final question to the pile. The morning was so cold that every breath was visible. A small team gathered in the squash court. Scientists, a few military observers, and workers who had come to trust the quiet intensity of this basement project. Fermi stood by the control panel, notes neatly organized. He looked like a man about to conduct a routine experiment, not a man about to reshape the future. One by one, the control rods were withdrawn in measured increments. After each step, the detectors clicked faster. The graphs climbed. "Take it out another 12 inches. Fermi said softly, watching the instruments with the focus of a sailor watching the tide. The multiplication factor crept toward 1. Time seemed to stretch. Everyone present felt the world narrowing to the line on a chart. At 3:25 p.m., Fermi made a small gesture with his hand. "This is it," he said, not loudly, not triumphantly, simply matter-of-factly. The detectors rose steadily, without falling back. The pile had reached criticality. A controlled, self-sustaining nuclear chain reaction was alive beneath the stadium in Chicago. For 28 minutes, they allowed it to run. Outwardly, it was anticlimactic. No flash, no roar, only the quiet acceleration of neutron counts and the awareness that an invisible fire had been ignited and held in human hands. Then Fermi ordered the rods reinserted. The reaction died as obediently as it had begun. Someone opened a bottle of Chianti. Paper cups were passed around in a gesture of communal celebration. Compton, the project leader, phoned Washington with a coded message. "The Italian navigator has landed in the New World." Fermi, the Italian navigator, listened without showing much emotion. His gaze remained fixed on the pile, with a fondness tempered by pragmatism, like a gardener observing a seed that has sprouted out of season. Outside, students hurried past Stagfield, oblivious. Snow began to fall in small, gentle flakes. The city continued with its ordinary rhythms. Yet in that basement court, a door had been opened. Proof that humans could initiate and control the power within atoms. And proof is never the end. It is a beginning with far-reaching consequences. One CP. One had demonstrated the chain reaction could be controlled. The project transitioned from a question to a task. Fermi felt a shift like a change in the ambient temperature. In the month that followed, the makeshift squash court experiment gave way to industrial urgency. The Met Lab expanded. Recruits flooded in, and Chicago's winter corridors buzzed with a new sense of purpose. CP-1 was dismantled and rebuilt as CP-2 in a safer location outside the city. Reactors were no longer curiosities. They were becoming essential infrastructure. Fermi navigated this transformation with peculiar dual perspective. He could simultaneously appreciate the elegance of the underlying physics and the blunt reality of its applications. He never pretended they were separate. He would stand at a chalkboard explaining diffusion equations for neutrons, then turn and inquire whether the graphite shipment met the required purity specifications. He performed calculations on scraps of paper while walking to meetings, not out of love for paperwork, but because every number now carried significant weight. The idea of a pile evolved into the more precise term reactor, to maintain a stable chain reaction, a geometry that balanced multiplication, and leakage was needed, moderators that slowed neutrons without absorbing them, and control systems that could respond faster than human reflexes. Fermi's understated genius was to make these requirements seem like a natural extension of the laws of physics. His reactor designs weren't battles against physics. They were collaborations with it. Concurrently, the broader Manhattan Project was racing toward the creation of a weapon. Los Alamos in the desert became the central hub where bomb designs were refined. Fermi spent time there as well, contributing to discussions with the same calm precision he had displayed in Rome. Colleagues remembered him as someone who could resolve disputes by returning to fundamental principles. When meetings became heated, Fermi would scribble a few lines, look up, and say something like, "Let's compute the order of magnitude." It was an almost magical phrase. It reminded everyone that nature was indifferent to their egos. In July 1945, he witnessed a Trinity test in New Mexico, the first detonation of a nuclear bomb. He stood several miles away with paper scraps in his pocket. As the blast erupted, a light resembling a second dawn, a shockwave rolling across the desert. Others watched in either awe or dread. Fermi conducted a small, practical experiment. He tore the paper into small pieces and released them as the shockwave arrived. By measuring their displacement, he estimated the bomb's yield. The gesture was so characteristic of Fermi that people later chuckled about it. Even on the precipice of potential destruction, he was still engaged in physics. But laughter didn't equate to comfort. In the aftermath of Trinity, events unfolded with alarming speed. Hiroshima, August 6th. Nagasaki, August 9th. The war concluded under a mushroom-shaped shadow. Fermi didn't seek public recognition. Yet privately, those closest to him sensed a somberness. He had helped unlock a door. Now he was confronting what had emerged. Back in Chicago after the war, he returned to teaching and the quieter pursuits of science that felt like a breath of fresh air. Students flocked to his lectures, not because he was theatrical, but because he illuminated the subject matter. He lectured on beta decay, the statistical behavior of particles, and the strange interplay of chance and determinism in quantum systems. He had a knack for making nuclear physics sound like a story the universe was slowly narrating, not an enigmatic puzzle designed to exclude the uninitiated. His own work continued to shape that narrative. During the war, he had already advanced the understanding of neutron scattering and reactor kinetics. After the war, he shifted his focus to particle physics and cosmic rays, helping to establish the foundations of what will become the standard model. Yet the reactor remained his most tangible legacy. It was the pivotal link between his early curiosity and the world's new reality. Fermi wasn't naive about the dangers. He participated in committees that advised the U.S. government on nuclear policy. He advocated for international control of atomic energy, believing that a fire of this magnitude couldn't be safely managed by a single nation. Some colleagues considered him cautious. Others thought he was overly trusting. Fermi, as usual, remained steadfastly empirical. He recognized that human nature possessed its own set of constants: fear, pride, hope, miscalculation. If these constants were integrated into equations involving nuclear weapons, the results could be catastrophic. In 1949, when the Soviet Union tested its first atomic bomb, the world balance shifted irrevocably. Debates arose concerning the development of a hydrogen bomb. Fermi opposed rushing into it, warning that a weapon of that scale could erase any distinction between war and total annihilation. His opinion carried weight, but not enough to prevent the H-bomb program from moving forward. Fermi remained engaged in the discussion, not to endorse it, but to ensure that reason didn't completely abandon the room. Despite the gravity of the situation, he remained a gentle and approachable person. He enjoyed hiking in the mountains, joking in multiple languages, and playing with his children. He had a habit of whistling while he was thinking. Laura once wrote that his mind seemed to find rest when his hands were occupied with something ordinary: sawing wood, fixing a radio, arranging books on a shelf. Perhaps it was his way of reminding himself that the world was composed of more than just nuclei. In the early 1950s, he began to feel unwell, stomach pains that he ignored for too long, because he'd never been attentive to his own body. By the time doctors discovered cancer, it was progressing rapidly. The news didn't evoke sentimentality in him. It spurred him to be efficient. He organized his papers, met with his students, and finished unfinished conversations. On one of his final walks on the Chicago campus, a student approached him hesitantly and asked him what he considered to be the most beautiful idea in physics. Fermi paused. He looked at the trees, their leaves changing with the season, and said that nature is simple when you look at it the right way. He didn't mention atoms or reactors. He meant something more profound, that beneath the complexity there's an underlying order, and that order, once understood, can provide stability. Enrico Fermi died on November 28, 1954. He was 53 years old. For someone whose work had impacted the world so profoundly, his death was a quiet, personal affair. Family at his side, colleagues stunned not by grand drama, but by the absence he left behind. The projects he had initiated continued without him, because physics is inherently a communal endeavor. Yet his approach, clear, deliberate, and grounded in reality, persisted as a guiding principle within the discipline, a way of interacting with nature that future generations learned to emulate. The reactor was now a tool in many hands. It could illuminate cities, power submarines, produce isotopes for medical applications, or fuel new weapons. Fermi had always understood that knowledge is like the wind. It doesn't choose which sails it fills. But he also believed that humans were not powerless in the face of that wind. Control rods existed not only in graphite piles, but also in ethics, cooperation, and vigilance. The question he had once posed in a basement had been answered. Now the more challenging question was the one that history would continue to ask. What do we do with the answer? Years after Fermi's death, he began to be remembered in two conflicting ways. One voice hailed him as a father of the atomic age, a man whose calculations paved the way for reactors and bombs. The other voice recalled him as a teacher who could instill understanding in a room, simply through his clear explanations. Both views were accurate, yet neither fully captured the whole truth. Fermi had always inhabited the intersection of theory and reality, between the elegance of a law and the weight of its consequences. In Chicago, his former students dispersed across universities and national laboratories. They carried the Fermi style with them like an inherited toolkit. Begin with simplicity, estimate carefully, stay grounded in data, and distrust unnecessary complexity. In a scientific world increasingly dominated by abstraction, this style provided a kind of moral compass. It didn't. He wouldn't dictate what to think, but rather how to maintain intellectual honesty. Meanwhile, nuclear reactors became increasingly common. The first civilian power reactor in the U.S. became operational in the early 1950s, and other nations soon followed suit. The concept that began as a graphite structure beneath a football field was now situated along coastlines and riverbanks, quietly operating within concrete domes. For some, this represented hope. Electricity without the pollution of coal, isotopes for cancer diagnosis, a future potentially eased by abundant energy. For others, it signified a persistent threat, an invisible power susceptible to leaks, meltdowns, or weaponization. Fermi would have understood both perspectives. He never believed physics inherently guaranteed progress, but rather expanded the range of choices. A reactor was a controlled chain reaction, but maintaining control required cultural maturity, as much as cadmium control rods. This meant well-trained personnel, stringent regulations, transparent communication, and the humility to halt operations when anomalies arose. The same delicate balance between a multiplication factor of less than one and more than one applied to institutions, negligence in one area, secrecy in another, and suddenly the margin for error would grow exponentially. In the 1970s and 80s, public discussions regarding nuclear power intensified, particularly following incidents such as 3 Mile Island, 1979, and Chernobyl, 1986. People protested, debated in parliaments, and expressed their concerns through music. Had Fermi been alive, he likely would have calmly analyzed the situation, inquiring about the specific events within the reactor core and the failures within the human systems involved. He would have insisted on distinguishing between genuine fears and irrational hysteria, without dismissing the validity of those fears. His character was perfectly suited for such careful and empathetic analysis. The scientific community also began a more explicit reflection on responsibility. Fermi's generation had entered a wartime emergency, believing they had to develop the atomic bomb before a potentially more dangerous regime did. After the war, the central question shifted from can we to should we, again, and if so, how? This transition became integrated into the ethical education of physicists. Fermi's life was often examined as a case study, not because he was a straightforward hero or villain, but because he was a human being who strived for clarity amidst immense pressure. Beyond this, there was the enduring legacy of his scientific contributions. The Fermi theory of beta decay, His work on Fermi-Dirac statistics and his later contributions to particle physics continue to shape new discoveries. Future generations associate his name with constants, equations, and paradoxes, landmarks in an ever-expanding field of knowledge. His approach to nuclear physics paved the way for neutron transport theory, reactor design methodologies, and the practical geometry of critical assemblies. Even in laboratories where the sound of his voice had long faded, his method of observing nature was still employed. Laura Fermi lived long enough to witness the global debate surrounding her husband's work. She authored memoirs that focused less on high-level politics and more on the nuances of their daily lives. Enrico's absent-mindedness regarding keys contrasted with his meticulous precision with neutron cross-sections, his relaxation through building shells, and the joy that lit up his face when a student truly grasped a concept. These memories grounded him in reality, reminding readers that the atomic age was not created by mythical figures, but by ordinary people who shared meals, told jokes, worried about their children, and sometimes made misjudgments about the future. In the early 21st century, nuclear energy reemerged in discussions as the urgency of climate change grew. Some nations expanded their nuclear reactor capacity, while others opted to phase them out. New reactor designs, small modular reactors, advanced coolants, passive safety features, promised to make the chain reaction more controllable than before. The debate shifted from the existence of the power itself to humanity's ability to manage it responsibly. In that debate, Fermi's presence was strangely palpable, not as a slogan but as a methodology. His legacy whispered, "Focus on data, not headlines. Rely on evidence, not fear or zealotry. Recognize that tools are neither inherently moral nor immoral, but consider the hands that wield them and the systems that guide their use." Imagine him, if you will, walking again along a river, older now, his coat collar turned up against the wind. The river represents energy. It has a capacity to erode cliffs or power mills, flood cities or irrigate fields. The physics of the river is impartial, but humanity's relationship with it is not. Fermi, who once admired simplicity underlying flowing water, would likely still be pondering the question Giulio posed. Why does it keep going? And his answer would likely remain the same, twofold. Because nature allows it, and because humans choose how to utilize that allowance. He didn't provide a simplistic moral conclusion, but rather a more refined question. Today, if you walk through the University of Chicago, the former Stagg Field is gone. Its stands were demolished long ago. The area has been resurfaced and repurposed. Students hurry by with backpacks, and leaves gather in the corners. The place appears peaceful, almost unremarkable. Yet beneath that normalcy, there's a subtle echo, not of noise, but of a moment when a small group of individuals discovered how to contain the power of a star within a human-made structure. This echo is not supernatural. It is historical. It serves as a reminder that revolutions do not always arrive with fanfare. Sometimes they occur in a basement, with graphite dust on your shoes and a calm voice saying, "Another 12 inches." Fermi's story at its heart is not solely about nuclear physics. It is about the harmonious coexistence of precision and humility. He was a man who trusted nature enough to question it, and trusted people enough to teach them how to listen. That combination is a rare one. Many geniuses guard mystery jealously. Fermi moved in the opposite direction, aiming to make understanding a shared pursuit. In the years since his death, physics has delved deeper into the atom and far beyond it, into quarks, neutrinos, black holes, and the earliest moments of the universe. Each generation develops new instruments, theories, and metaphors. Yet if you trace the lineage of methodologies, you'll often find a quiet Roman thread running through them. The habit of estimating before overcomplicating, the respect for data over drama, and the willingness to be wrong in order to accelerate learning. These are not only scientific virtues, they are human ones. And the reactor, his most tangible legacy, remains at the crux of our choices. It is neither a savior nor a curse, but a tool shaped by a mind that valued simplicity. The chain reaction within a reactor serves as a lesson written in neutrons. Growth must be balanced by restraint. The same principle applies beyond the reactor core. Every technology that amplifies human power also amplifies human responsibility. Control rods are not optional. When people speculate about what Fermi would think today, about nuclear energy, about weapons, about the world's precarious political situation. There is no single definitive statement he left behind. However, there is a style of thinking he exemplified. He would begin with facts. He would estimate. He would differentiate between the known and the feared. He would treat uncertainty as something to map, not something to blindly accept. And lastly, he would remember that while numbers describe nature, ethics define us. Perhaps that is why his life still resonates as a story worth telling in a quiet tone, because it is not a tale of a man who conquered matter, but a man who learned the language of matter and taught others how to hear it without sacrificing their own humanity. In a sense, Enrico Fermi never stopped walking along that river he cherished as a boy. The river expanded into oceans, into university basements, into deserts illuminated by blinding light. But the central question remained consistent. Why does energy perpetually flow, and how we manage its momentum? The world continuously answers, in 5 parts and 50 more. And somewhere within that answer, you can still sense the steady hand that transformed the scientific maybe into a controlled, cautious yes.